Let's first recall what we talked about in the pre-class lecture on validation. Here we said validation relies on the following chain of reasoning. And that reasoning is about how big we set k. We saw when we set k to a small amount, that is to assign a small amount of data for validation, that we are saving most of the points for actually computing the hypothesis. Therefore, the size of h and h bar are approximately the same, and that makes this part of the equation true. On the other hand, we also saw that if we set k equal to some large amount, that means our validation cost is actually quite accurate and will be a good approximation of the actual test cost. Of course, this is for the hypothesis that is generated just with the h minus, that's the set of points that are left over, the m minus k points that we are using to determine the hypothesis here. So this part of the equation is true in this case. So a question for us is to think about whether we can get all parts of this equation to be true. Could we have a k that's both set to big and small simultaneously? And although that sounds like an implausibility, it really is the case that we can have our cake and eat it too. And we can set it both to k being small and big, with some important caveats. Let's see how that works. Let's consider the case of leave one out cross-validation. This is a version of validation where we just use 1 point for validation, so we set k to as small a number as possible. Just 1 point. In fact, we did this at the beginning. In our pre-class lecture on validation, we talked about how to estimate the test error based on just 1 point. We said 1 point isn't very stable, we'll get high variance, so we're going to move to k points. In leave one out cross-validation, the idea is to exactly choose one of these points out of the total m possible. Let's call that point CV, and take this point out of the training data set and use it just for validation. And then in this case, when we go to do the learning, we are going to learn with this new data set CV, which just has this CV point subtracted away. We're going to learn a hypothesis H minus, but we're going to denote it specifically as the H minus that's due to this particular missing point CV. Okay? And the important part about this is we're going to execute this a number of times, right? We're not going to do it just for one case, but do cross-validation, which means we're going to conduct this type of experiment all m possible times, where the CV point is rotated from the first point to the second point, all the way to the mth point at the end. That means we'll have a total of m experiments, each of which has a unit point to do performance on. So in binary classification, you would either get the point correct or the point wrong. And we would average all of those costs to get a average cost, which would be our leave one out cross-validation cost. This is the case where we're almost using all m examples for k, because we are actually going through all k points and using them each in turn as a single point for testing and validating on a total set where k equals size of m. But there's a caveat here, of course, because all of these particular h minuses are actually quite correlated with each other. For example, when h minus CV equals 1, point 2 through point m are all in the training data set, and when we rotate it to point 2 being CV, that means point 1, point 3, all the way to point m are in the training data set. So these hypotheses are highly correlated. They're not independently drawn, and so it's not as nice a case when we can use k points for validation in total. Let's take a look at cross-validation in action by looking at this familiar example of univariate regression. Here we're going to learn a target function of class H1, which means a linear line with slope and intercept. And we're going to choose, in this case, a data set of size 3. When we do leave one out cross-validation, that means we're going to pick 2 points for training and 1 point for validation. Let's see how this works. We're going to rotate each time deciding which point to validate on. Let's call this the first point that we're going to pick for our validation. So this will be our validation set. These two will be our training set. So when we draw the line, it might look like this. And the amount of error is then, for this particular point that is on our test set, this amount. This will be our j, pointwise j, for CV equals 1. We'll now rotate this point to be validation, and we'll draw a line through the other 2 points, which will be our training set. This is our cost when JCV equals 2. Now let's rotate our third point for validation. Again, we'll draw a line through, and we'll obtain a third cost for this one. What remains then are all of these costs that we have for the individual cross-validation folds, and we're going to take their squares, sum them together, and that will be our cost for the cross-validation from leave one out. And we can see this here as well. Just as we saw in the previous video, we saw we could do model selection using cross-validation. That's here even in this toy dataset as well. Here we're looking at the case of these 3 points as a dataset and trying to assess which model would work better. Maybe a linear model of H1 would work well. But because we have so few points, maybe we believe a constant model of H0 might work better. So which one would actually work well? We can measure that using cross-validation as well as regularization. In cross-validation, we just calculate all of these errors, and we would do it for the constant model as well. We can see that the line segments lengths in H0 are shorter, so we have an empirical validation. Our cross-validation actually shows that the constant model is a better fit for this data set. It does this by peeking at the test performance on the validation set. So that was leave one out cross-validation. But leave one out cross-validation happens to be pretty expensive for large data sets. I think you can understand why. The idea is we would have to validate all m times according to our data set. That means we would have to train m classifiers with all m points minus 1. That means our training time would be increased by a linear factor of m. When training can be very expensive, for example in the case of deep neural networks, that becomes a very expensive proposition. So what can we do? There are other ways to do cross-validation. Cross-validation just basically means reusing the same dataset and validating on different parts. We don't have to do leave one out where we set the k to size 1. We can set it to a larger number, for example, determined by how many pieces we want out of our dataset. Here we can see we have tenfold cross-validation, where each part of the dataset is cut up into an equal number of instances of 10%. We'll use one part for testing, or in our case, would be the equivalent of validation. and we'll use the remaining 90% for training purposes. What happens next? Well, that was just one fold, so we've tested the system one time with a hypothesis that just excludes the validation slice. So we want to rotate this validation slice over to the next one, so we'll do that. When we rotate it over to this slice, this means that this will serve as our validation data set, and the rest will serve as our training set. We can obviously rotate this slice to the next one and the next one, performing a total of 10 different experiments with 90% of the data for training and 10% for testing. As we go for larger and larger k, the pie slice gets smaller, and we are approaching leave one out cross-validation again, introducing the factor overhead in training multiple classifiers on datasets approaching the size of the entire dataset. Therefore, many times we recommend the simple setting of just using 10-fold cross-validation, which gets us a fairly robust estimate of the validation costs by using 10 different estimates rotated over this 10 different slices of the data set. In summary, now let's talk about cross-validation as based on validation, the key ingredient that we use to combat overfitting. The idea is that in validation, we try our best to estimate the validation error. We saw that there was a trade-off when we set the k equal to a large amount, where we're able to estimate our validation costs accurately, but then the hypothesis that we are trying to get with our smaller shrinked training set is going to be less stable. When we use a smaller number for k, then our estimates of the validation error will be less stable, although we'll have better performance of our H- classifiers. We fixed this in cross-validation by doing this estimate multiple times. But we saw that when we do this, it breaks an independence assumption. The different cross-validation errors are not independent of each other because their training data is actually correlated. When we have k-fold cross-validation, each of the points will appear in the training data of k-1 of the classifiers. We also saw that it introduces the factor of efficiency as a trade-off, because now when we do cross-validation, we are conducting multiple experiments, training on set sizes approximating the entire data set. And for you to think about, how else can we produce estimates of the testing cost? This is not the only way, but this is the one that's going to be introduced at this point. Later, when we get to random forest and the notion of bagging, we'll be able to produce other estimates of the test cost. In two separate parts, in this video and the video before, we saw how validation actually helps us do model selection. We saw one case in which we were trying to decide the number of features between a smaller amount and a larger amount and pick in terms of complexity. The other case which we saw in this video was the case between H0 and H1. And we saw in that case, the H0 classifier did a better job of having less error in their cross-validation. So we would have chosen H star to be H0 in this case and return the constant model as the classifier of choice